Okay, two more. This one we're going to go from grams to grams. This is the same thing that you did in part 3 of the introduction activity. I think, yes, in part 3, the introduction activity. And again, I'm going to use this reaction because it's got a nice mix of coefficients, and the same basic idea can be applied to any reaction that you're going to be doing. So the question that we're going to answer now is that if we had 1.50 grams of oxygen gas, we want to know how many grams of CO2, carbon dioxide, that will produce. So, just like we have been seeing, we start off with the value that we are given, 1.50 grams of oxygen times blank. Because we have the mass, we need to convert to the moles so that we can do our mole-to-mole conversion. A mole-to-mole conversion, reminder, is going to be done in every single stoichiometry problem you do. So the mass of oxygen off the periodic table is 32 grams of oxygen is equivalent to 1 mole of oxygen. Now we can set up and do our mole-to-mole conversion. Based on our balanced chemical equation, we see that we've got 11 moles of oxygen. That allows us to cancel out this unit, and that is equivalent to 8 moles of carbon dioxide gas. And because the question's asking for the mass of the carbon dioxide, mass is always measured in grams for us. We're going to take it one more step, and we're going to say 1 mole of carbon dioxide is equivalent to 44.01 grams of carbon dioxide. Again, we're adding this up off the periodic table, and anytime you add up off the periodic table, that is equivalent to 1 mole of that compound. That allows us to cancel out our moles of CO2. Forgot to cancel out our grams of O2. And the only unit we're left now is grams of CO2, grams of carbon dioxide, which is what we are looking for. And we end up with 1.50 grams of carbon dioxide. I know, weird. But it just so happened the way I set this up, the mass of oxygen is equal to the mass of carbon dioxide. Why? Because the math tells us that. So when we set up our conversion correctly, that's what we get. I'll leave this up, and we'll look at the last problem we're going to do in this series. If I had 4.67 times 10 to the third grams of water, so that's 4,670 grams of water. And I wanted to know how much of this compound reacted to form that. So a certain amount of this compound is going to react to make our 4,670 grams of water. To figure that out, we start off with the amount of water that we have. 4.67 times 10 to the third grams H2O. Our first step is to make sure that we are getting into the unit of moles so that we can do our mole-to-mole conversion. We add up off the periodic table. The mass of water is 18.02 grams of H2O, and that's equivalent to 1 mole of H2O. Again, it's called a molar mass. 1 mole of the compound is going to equal that many grams of the compound. We can now do our mole-to-mole conversion. We see that for 14 moles of water, and it's going on bottom so that we can get our units to cancel out. Oh, let's cancel out these units here too. That is going to be equivalent to 4 moles of the starting compound, C4H7O4. Now, because this is in the unit of moles, and we want to know how many grams, we got one more step to do. And we're going to add up off the periodic table. And when we add up off the periodic table, it's 1 mole, C4H7O4. Again, molar mass, it's 1 mole. And that has a mass, when you add it up, of 119.11 grams of C4H7O4. That allows us to cancel our moles. The final unit that we're left with is grams of that compound. And when we calculate it out, we get 8.82 times 10 to the third grams of C4H7O4. So the basic setup on all of these was the same. It's just how much work do you have to do. In gram to gram conversions, they tend to be the longest because you have the most conversions you need to make. But the one thing that every single one of them has in common is that you always have a mole to mole conversion. Anytime that you are going between two different substances, and each one of these is a different substance, you have to do a mole to mole conversion. That mole to mole conversion is going to be different for every reaction. So if I had a different set of compounds, if I had a different compound here, but it was still a combustion, I'd probably have a different set of coefficients, which would give me a different ratio here and give us different values. But the basic setup is always going to be the same.